Hello, this is our video demonstration for assignment 2, the Deep Space File Transfer Protocol. We'll be showing off both stop and wait and go back N protocols. Let's begin with a quick architectural overview. The system consists of two main components. On the left, we have the sender class, which represents the Mars rover. It reads the input file and sends it over UDP. On the right, we have the receiver class, which represents Earth station. It listens for packets, writes them to a file, and sends acknowledgement or ACKs. We also have the provided utility files. dsPacket enforces the 128-byte packet contract, and Chaos Engine simulates ACK loss and packet reordering. First, let's demonstrate a clean transfer with no packet loss using stop and wait. To start a receiver, we only need a few things: the sender IP address, the sender's ACK port, the receiver's data port, the output file name, and the reliability number RN. Entering the command, the receiver starts, listening on its data port 8888 with a reliability number of 0, meaning no ACKs will be dropped. For a sender to connect to the receiver, all they would have to do is, in their own terminal, input the receiver IP address, the receiver's data port, the sender ACK port, the input file, and timeout in milliseconds. The command also has an option for window size used by go back N, which will be demonstrated later. For testing, the input file contains a short excerpt from the B-movie script. After running the command, we can see the handshake complete successfully. The sender then transmits each packet and waits for its individual ACK before sending the next. Finally, an EOT packet is sent and acknowledged, completing the transfer cleanly. Now let's see how the protocol handles a more realistic, unreliable scenario. We'll restart both programs, this time setting the receiver's reliability number to 3, which instructs the Chaos Engine to drop every third ACK. We run the same sender command again. Now we can see the transfer begins normally, but when it reaches the third ACK, the Chaos Engine drops the ACK for packet 2. The sender, waiting for this ACK, eventually times out and retransmits the packet. The receiver, now expecting sequence 2 again, accepts it, delivers it, and sends a new ACK. The protocol gracefully recovers, demonstrating correct RDT 3.0 behavior. Let's demonstrate the higher performance go back N protocol. We'll use a different, slightly larger file to better illustrate pipelining. The file we'll use for this is the transcript for a Vsauce video, specifically the napkin ring problem. We'll start the sender with a window size of 20, enabling go back N. That means the sender will fill its window with up to 20 packets before waiting for an ACK. Notice the difference. The sender pumps packets into the pipeline. The receiver buffers any out-of-order packets, but only sends back a single cumulative ACK for the largest contiguous chunk of data received. This is much more efficient than stop and wait. Finally, let's do a quick demonstration of the go back N protocol with the Chaos Engine dropping every third ACK. Running the same sender command again, we can see that the protocol works just as well without any faults. Now, a reliable protocol isn't just about the logs. The most important part is the file arrives intact. So let's verify. This is the first input file used in the stop and wait protocol. This is the first output where it was a clean transfer. And this is the second output where every third ACK was dropped. This is the second input, which was used in the go back N protocol. This is the first output, which was a clean transfer. And finally, this is the second output, where every third ACK was dropped. As we can see from the quick overview, the files are identical. Our DSFTP implementation successfully and reliably transferred the file using both stop and wait and go back N, even in the presence of simulated packet loss. This concludes our demonstration. Thank you.